Now, since we're done deriving the formula for conduction through hollow cylinder and hollow spheres, we can now solve an example or a problem that involves such kind of conduction. So here we have a hollow cylinder, or specifically a pipe, which is IC310. So the details are included in the problem. You may want to pause this video for you to understand the problem clearer, and go back after you've read and analyzed the problem. Okay, so I assume that you've read the problem and have understood what is required by such kind of problem. So in this case, the problem asks for the heat conduction per unit length. So in this case, the heat per conduction is Q. Heat of conduction is Q, or it is simply the heat rate. And then, if it is per unit length, then we're actually we need to find this Q over L. So in the equation before, we've presented the Fourier equation, which is Q over A is equal to negative K dt over dx. And then, upon derivation, we've arrived in a formula for our heat rate, which is equal to K, negative K log mean area, and then the difference in temperature divided by the difference in the radius or the radii of our hollow cylinder. Now, if you want to write it in an easier way so that we can remember the formula, we can just simply substitute the logarithmic area, which is the ratio of the difference of the area to the logarithmic difference. So that becomes negative K, and then this becomes multiplied with 2 pi L, and then we have the difference in temperature divided by the ln of R2 over R1. So this also means that this is the difference in the logarithmic area. So in this case, if we're talking about Q over L, we might need to probably just divide both sides by L so that we can place the L right there. Okay? So, pag nilipat natin siya, mangyayari sa ating final equation would be Q over L equals negative K, and then multiplied with 2 pi difference in temperature, and then the radius or the radii. So in that case, we'll be using this formula to find our Q over L, and that's fairly easy. But the only thing that we need to determine is our radius or the radii for this figure. Now remember, T2 minus T1 is simply the difference between these two temperatures, and then we also don't have our thermal conductivity, so we need to find those things. And the tricky part here is knowing what are the values or the given for such problem. Okay, so let us take a good look at the problem. It says here that we have an IC310 pipe, and it is in an 8-inch schedule 60 stainless steel pipe. So let's try to evaluate first find the radius first, since it is a lot easier to find this on our table. So we'll be using our Paris Handbook again, and we'll be looking for our 8-inch schedule 60 stainless steel pipe. So in your Paris Handbook, you can browse over chapter 10. So in chapter 10, this is the transport and storage of fluids. So I'll be linking, or I'll just be writing somewhere here about Paris Handbook 9th edition, so that you have the reference. But you can notice here there are a lot of flow meters and all the stuff that is related to storage of fluids. And what you need to browse over is this section, which is 10-79, and table 10-22, which is the properties of steel pipe. So if you can see, there are a lot of columns here: the nominal pipe size, outside diameter, schedule, wall thickness, inside diameter, and all these properties. But the most important thing that we need to remember is that if we're given a pipe size, that's almost the same as saying that that is the nominal size of that pipe. In this case, since we were given the 8-inch schedule 60, it only means that we have a nominal pipe size of 8 inches. So in this case, we need to find where is this 8 inch. So this is the 8 inches, the nominal pipe size, and then it says here that it is schedule 60. So we need to find here where is the schedule 60. So this is what we call the schedule number. This is 5S, 10S, 20. S means that it is taken from the ASME standards, okay? And the ST here, it only means that it is like standard thickness, so something like that. The XS is extra strong. So you can also take a look at the footnote after this table to understand what's the meaning of each the abbreviation. But technically, the numbers that are indicated here are the schedule number. So 5S means it is 8-inch nominal pipe, schedule 5, schedule 10, schedule 20, and in this case we need the one that is at schedule 60. Okay, so a schedule 60 pipe has an outside diameter of 8.625 inches. So in this case, if that is our outside diameter, then that only means that our R sub 2 is equal to 8.625 inches. Now, this is the wall thickness in inches. We're given with a wall thickness of 0.406. So therefore, if we have, let's say, this pipe with an outside diameter of 8.625, the thickness, the wall thickness should be this value, 0.406. So from that value, you can already determine the R sub 1 by simply subtracting 0.406 times 2 with this outside diameter. But Paris Handbook also already gave the exact value for that for the inside diameter, which is 7.81. Sorry, by the way, this is in diameter, so we need to actually divide this first by 2. So, sorry. So, in that case, we have 7.813. So, that is 7.813 inches, then divided by 2. So, this is our radii. So, for the first one, we have 4.3125 inches. And then for the second one, or the shorter radius, or the inside radius, we have 3.9065 inches. Okay, so now since we already have the R1 and R2 based on this equation, then we just need to find our K. Now, as you can remember, K is dependent on the material type. Okay, and of course, it is dependent on the average temperature of our system. So in that case, if you want to check on the average temperature, then you might as well want to take the average of 4 degrees and 25 degrees Celsius. So that is simply equal to 14.5 degrees Celsius. Since that is the average temperature, so let's simply convert this in degrees Fahrenheit, since our units here are in English. So we'll be solving this problem in English units. So upon conversion of 14.5 to degrees Fahrenheit, we get 58.1 degrees Fahrenheit. So I will not be digging much deeper in your conversion skills. You can always review that and solve for problems that involve conversion. So with that, let's take a look on a certain table in your Paris Handbook so that we can determine the IC310 pipe. IC means the American Iron and Steel Institution, I think, if I'm not mistaken. Okay, so let's go over section chapter 2, physical and chemical data, and let's go over. If you can see the contents here, there are a lot of physical and chemical data. Okay, it goes from the physical to the densities and all these solubilities, but the most important thing here is under this um, under the thermal conductivities, which is also under 2-460. So we've already used this table before, table 2-326, and if you will browse for the next pages, you will get a lot of thermal conductivity temperature tables for metals and all other metals, including the alloys. So if we're talking about steel, especially those with a which have the types, then we're talking about the alloys and usually chromium alloys. Okay, so it because makes the it makes steel a stainless when it has a lot of other components, especially the chromium. If the carbon the Usually the carbon steel means that it has a high carbon content, but if it goes higher than that, then we can simply say that it's a cast iron. So a lot of pipes differ in the properties, especially the materials used in its construction. So we have to take note of that and consider it as the very foundation of finding the thermal conductivity. But in case if you're given only a problem in which it says that it is a steel type, then you can usually assume that that it is an iron with something like a small amount of carbon. So with that, let's take a look on the IC. This is the American Iron Institute type number 310. So that is this one, 310. And that is if it is 212 degrees Fahrenheit, that is 8. And then if it is 932 degrees Fahrenheit, then that is 10.8. So with that, as you can see here, our K is at 212 degrees Fahrenheit, and here this is 932. That is really small compared to that is really a very high value compared to our average, which is just 58.1. So yung average nga natin hindi pa umabot ng 212. So with that, we need to extrapolate the values for our thermal conductivity. But if ever your answer would be something like would be negative, because extrapolation is just a linear function. So in that case, it's not sign sensitive to the sign of our values, no. So with that, let's try to extrapolate, no. You can extrapolate with me so that you can practice your skills, no. So I'll be going to this stat and then the a plus bx again, or the linear equation. So remember, you can always browse this extrapolation in the previous video. Okay, so with that, with 58.1 degrees Fahrenheit, I obtained a thermal conductivity of 7.4015. So the unit here is given, and it is in English, BTU per feet r degrees Fahrenheit. So that is BTU per r feet and then degrees Fahrenheit. Okay. So in this case, we already have the complete values for our equation. We can now simply substitute these values so that we can finally find the answer for the heat rate in each unit length. Sorry. So we get Q over L. This is equal to negative 7.4015, then 2 pi. If you wanted to make sure that you have obtained the correct answer, then you might as well want to include the units when you're solving. So I'll not be including the units in this solving para magkasya mismo, kasi pag nalagay ko yan medyo mahaba, so baka hindi magkasya sa screen. So 2 pi, and then T2 minus T1. This one, we need to convert the temperatures in degrees Fahrenheit first so that we can determine the exact difference, no? Or we can just subtract this temperature and then multiply it by 1.8, since if we're talking about the difference in Kelvin or in degrees Celsius, it is the difference just degrees Fahrenheit over 1.8. So, but just to make this clearer, no, I'll just be converting them in degrees Fahrenheit, no? So with that, when we convert 4 degrees Celsius in terms of degrees Fahrenheit, we get 39.2, and then 25 degrees Celsius is 77. Okay, so 39.2 and 77. So we can now write it 77 and 39.2. So remember the flow of heat. So heat travels from the higher temperature region to the lower temperature. So our T2 here should be the lower one. So we get, so divided by the ln of the higher radius, which is 4.3125, then divided by 3.90665. Okay, so with that, the answer here is, you can also calculate so that we can double check our answer. And if your answer is different than mine, then you can always ask me about it, or you can comment your solution or your final answer so that I can recheck it, since I'm just solving it right now. So the answer is 117,778.7303. So the unit should be British thermal unit per. So we've used R here, so that is R, and that is the heat rate, then per length, which is feet. So that is our unit. So remember this answer is in English. Okay, so don't confuse this with this is actually 17,778.7303. Okay, so what I was saying before is that if we wanted to use, let's just take the value here, the delta T here. So if we just evaluate this delta T, we get 37.8. So what I was telling before is that if you use the degree Celsius, you will get simply 25 minus 4. So that is the difference in terms of degrees Celsius or Kelvin. This is equal to 21 degrees Celsius. But since this is in English, you can simply multiply this by 1.8. So with that, we need to check on the answer. It must be the same here, 37.8. So pag kinalculate ko naman siya, so the answer is 37.8. So it's just the same. So you can use that method if you find it a little tedious to simply convert all the temperatures in terms of degrees Fahrenheit. So yeah, that's all for conduction through a hollow cylinder. So in this problem, I already introduced to you how we use the thermal conductivity in other tables, especially for the chromium alloys, and then this table here at section 10. So don't forget, it is a very important table, the steel pipe sizes. So baka kasi maka-encounter kayo ng problem, sabihin dito is 8-inch schedule 60, and then you'll just realize, bakit 8-inch lang yun? So, what I'm gonna do with that problem, kasi 8-inch lang yun eh, so, isa lang yung given. So, but technically, when we talk about pipe, it will always have a thickness, kahit sobrang nipis pa niya, ano. And by the way, this is a very high answer, kasi nga, kung mapapansin nyo, this is a very low temperature, 4 degrees Celsius and then 25. So, what happens is that, wala na tayong pakalam kung ano ba yung nasa loob nito, no? Kasi, ang mahalaga sa atin din is yung temperature nung material na to, no? Or nung fluid na ito, no? But of course it will be a different scenario in convection. But for conduction, we just need the temperature of whatever is inside this pipe, so that we will assume that the temperature of this fluid here would be the temperature of the inside diameter. We're not concerned with what's really inside this whole region here. Okay, so that's all for our conduction through a hollow cylinder.